Okay, I think we'll get started. Welcome everyone to the John and Susan Wierman lecture series in air quality data analysis. These talks feature development in air quality data analysis that are relevant for policy development. It brings together faculty and researchers in engineering, natural sciences, and with state and local air quality officials to enhance understanding and stimulate collaborations on important air quality issues. These lectures are intended to showcase new development, to encourage quantitative analysis of scientific issues related to air quality, and to elucidate policy implications of recent research. The lecture series was established by with a permanent endowment by the John Wierman and Susan Wierman. So now I'm introducing the speaker. Tracey Holloway is the Jeff Rudd and Jean Bissell Professor of Energy and Analysis and Policy at the University of Wisconsin in Madison, jointly appointed in the Nelson Institute, there it is, for Environmental Study and the Department of Atmospheric and Ocean Sciences. She's been recognized as a member of the National Academy of Medicine and as a recipient of the Ascent Award from the American Geophysical Union Atmospheric Sciences section. She serves as two-time leader of the NASA Health and Air Quality Applied Sciences team. Prior to joining the University of Wisconsin faculty in 2003, she earned a bachelor's degree in applied mathematics at Brown University, and then PhD in atmospheric and oceanic sciences with a graduate certificate in science and technology and environmental policy from Princeton University. Following graduate school, she completed a postdoctoral research fellowship at Columbia University Institute. So today her talk is linking data with decision making for air quality. Welcome, Tracey.
Thank you. Well, thank you all for taking the time to join today for the seminar, both in person and online. And thank you very much to Susan Wierman and John Wierman for hosting this event. It's been really a pleasure to be here on campus today and to meet students and faculty. My first time visiting Johns Hopkins, and I'm really impressed with this great institution. So before I get started today, I want to first recognize my group at the University of Wisconsin and also our funders. Really, we approach science as a team sport, and the work that I'm doing is representing the work of my team, including scientists Monica Harkey, Paul Meyer, Jenny Bradford, and Pat Reddy, recent graduate students, including Alicia Hoffman, Rashti Amin is actually here in the audience, Jinran Wu, and Jennifer McGinnis. And our work is supported by a range of government, nonprofit, and federal funding. The work I'm talking about today is mainly supported by NASA, the American Lung Association, and NRDC. So when we think about air quality, what we're talking about are chemicals in the air that pose direct risks to human health, ecosystems, visibility. And I'll be talking about how the science of air quality fits into a broader social context and some of the work that we're doing to bridge information needs with emerging science. But before I do, I want to contextualize this from an applied math perspective. As was mentioned, I did my undergraduate in applied math, and at Brown University, there's a lot of work in computational fluid mechanics. And the work that really made me excited about pursuing math-ish topics after graduation was a numerical methods class that was taught by your speaker yesterday, Dr. Ann Gelb at Dartmouth. So she taught my first numerical analysis class, and really that made me excited about the idea that you could use mathematical equations to capture the complex behavior of fluid systems and other nonlinear systems. And in fact, that really propelled me into graduate school, where I worked at the NOAA Geophysical Fluid Dynamics Laboratory. It's a large research center that was built in Princeton, New Jersey, to capture the capabilities of computers back in the 1960s and apply them to the massive nonlinear challenge of solving fluid dynamic equations relevant to weather. When we think about how computational fluid dynamics connects to air quality, my pathway in was through models, because as these fluid dynamic models were being used to simulate weather and hurricanes and climate, there was the realization that you could put in radioactive tracers just as one more variable in the model with a fixed lifetime and compare it with data from around the world from nuclear tests as a way to validate the models. But as they were putting in radioactive tracers, they said, well, we can also put in other chemicals that have other chemical processes. And over time, the relevance of these three-dimensional models to atmospheric chemistry and to air quality on the ground grew greater and greater. And today, the state-of-the-art model from the EPA used for air quality analysis is called the Community Multi-Scale Air Quality Model, or CMAQ. And my group runs CMAQ. This image is not from my group, but from the EPA's own work. But I think it really shows how you can run this model at finer and finer spatial scales and see more and more complex fluid dynamic behavior. What you're looking at here is ground level ozone, which we'll be talking about later in the talk. So one pathway from applied math to air quality is through numerical analysis and fluid dynamic modeling. Another approach is through machine learning and statistical methods. And I would say this has always been part of the air quality story. When we think about the health impacts of air quality, those are mainly deduced through statistical correlations between, for example, ER visits and outdoor air pollution. But more and more machine learning is coming into play to take satellite data and other data and merge it into high resolution estimates supporting day-to-day air quality forecasts and other applications. My group does not do a lot of we do no machine learning, but we do use statistical analysis in some of the other work we're doing. So there's kind of two main plug-in points for applied math to air quality analysis. But now I'm going to come back to the domain topic of air quality itself and think about where do the data sets come from and where are the issues that we're dealing with. And the gold standard for air quality data has been ground-based monitors, regulatory monitors. In the United States, those are implemented by states and tribes following guidance from the United States Environmental Protection Agency. These are carefully quality controlled, and there are a couple of thousand monitors across the United States, some located in the same place. And that covers a lot of ground, but it also leaves a lot of ground that doesn't have a monitor nearby. These are very expensive. I've heard kind of ballpark $100,000 to set up and about $25,000 a year to maintain. So that's really the limiting factor when we're thinking about why not just have more of these ground-based monitors. The second major data source used in air quality are these models that I mentioned earlier. They have become a very important part of the air quality management portfolio because you can test what-if scenarios in a model environment to see if they're going to have the desired impact. So before requiring some new technology on power plants, for example, you could simulate in this virtual environment what that might imply for the air that people are breathing and whether that's moving you close enough toward your goal for the cost. But the third data source in the air quality landscape is one that I'll be talking more about today, which is the role of satellite data for air quality management. And satellite data are kind of a newcomer to the air quality scene, in part because where air quality is regulated and managed by the EPA, in the United States, satellites are managed and sent up by NASA, by NOAA, that runs the National Weather Service, and sometimes by private companies. So trying to connect the dots between these research and weather-driven organizations and the needs of federal, state, and local regulators has been a big topic that I've been involved in, but I think it's a great example of the linking data to decision-making challenge that extends across other issues in air quality and certainly many other areas beyond. Anytime you're thinking about science, what you're really talking about is how to link to implement the science in a meaningful way, where you have the scientists of today, the scientists of tomorrow, and these individuals who are moving forward motivated by their own interests, by available funding, and by the context that they're being trained in. But when you're thinking about air quality, there's also a wide range of other factors, even outside the scientific community. And I think that's something that makes air quality an unusual field of science, because you have the data and the scientists, but you also have a lot of stakeholders, rules, and structures, especially in the United States under the Clean Air Act, which was signed in 1970. And just to kind of call out some of these indicators, we have regulated industries like factories, power plants, and car manufacturers. We have politicians and legislatures that may be taking regulations as a political topic, but in any event is certainly involved in passing and implementing rules. We have state agencies, and one of the interesting things about the Clean Air Act is that it is put in place by the federal EPA, but it is up to the states to meet those targets. And so it's a great example of federalism in action, where you have the states and the federal government working together. Each state has its own air agencies, and there's coalitions of air agencies. I think that's the logo of the National Association of Clean Air Agencies. You have nonprofits like the Sierra Club and others. You have community groups. You have those of us who are breathing air, especially vulnerable communities like babies and the elderly and kids who are outside playing and people with pre-existing conditions. And really, more and more, all of us are checking or maybe checking our air quality index on our phone. So the idea of thinking about air quality in the tech space and as a data that people may or may not be incorporating into their own lives is kind of an emerging issue. So when we're thinking about who are the decision makers, what does that look like? Sometimes it's easy when you think about science and policy to imagine that you have some academics who are marching to Washington, DC. But actually in air quality, and I think a lot of other fields, it's really a very complex ecosystem of interest and perspectives, many of which have just as much scientific expertise and much more than a lot of academic researchers. So it's not necessarily like us showing them, it's more like how can we learn what are the real issues from the experts who are involved in this from these different perspectives. Well, almost all of my work deals with air quality and working with partners. I don't think anywhere is it more front and center than in my role leading the national team for NASA called the Health and Air Quality Applied Sciences Team, which we call HACAST. And our website, hacast.org, is available and has recordings of all of our meetings, a lot of tools and getting started. For the context here, just to sort of give you an idea of our mission, the goal is to make, it's a NASA-funded initiative to make the billions of dollars in satellite technology relevant to organizations that can use it. And because NASA is not a regulatory agency, they don't have an agenda. They don't care really who uses the data. They just want to get it into the hands of users in the private, public sector, and state agencies for different organizations. When we're talking about what does NASA data mean, NASA develops models, they have distribution websites, they run some field campaigns, but the backbone of NASA data is really satellite data. And there is a constellation of satellites observing the Earth, what NASA calls Earth observations, and these have been in place for decades with the technology evolving. The newest addition to the portfolio of NASA data products is called Tempo. And Tempo is an instrument that launched in 2023. The data were only made publicly available in December. So this is very kind of new on the scene. But what makes Tempo data really exciting is that it provides hourly data during the daytime of invisible gases in the atmosphere, including nitrogen dioxide, which is mainly from cars and trucks, power plants, and industry, as well as formaldehyde, which is an indicator of evaporative emissions and volatile emissions like from trees and plants, as well as from household chemicals and industrial processes. There are other products from Tempo, but those are the two of the headliners. If you're interested in, this is just a simulated video to show kind of how Tempo is scanning the United States. But if you want to look at data from Tempo, there's a website that's really nice here, Tempo, you can read it, data_for public. And you can just by using a clicker and a slider, zoom in on air pollution of interest. And so I was preparing the slide deck yesterday. So I used Tuesday data. You can see here, this is just from the middle of the day, the plume of pollution going off the coast of New York over Long Island. And really you could look through the day, hour by hour, how that plume evolved and moved. This has been used for other, some notable dates you can see here, for example, like looking at the LA wildfires, because anything that burns emits NO2. And so you can see it from fires as well as from industrial processes in urban areas. So when we're thinking about this satellite data and who could use it, why might they use it? I have my own anecdotes and examples that I'll share with you. But I was really excited back at the end of 2003 when colleagues of mine in the UK did a social science analysis to look at how satellite data is perceived for air quality in the United Kingdom. And so this is a kind of a virgin territory, so to speak, because it hasn't been the audience that we've been cultivating through our NASA HACAST activities. And so I think it provides sort of a snapshot of maybe where the US was 10 years ago. They considered two groups. They called them Group A and Group B, but we can think of the Group A as scientists or researchers and Group B as stakeholders and data users. And one of the questions they asked was, do you consider satellite data in their current form to be useful to potential end users? And if any of you have worked in air quality or satellite data, it is not surprising to see the enthusiasm from the research community, where 87% of those surveyed said, yes, it is absolutely useful in its current format. But we can compare this with what the actual end users themselves thought, which is that only 32% said, yes, it was useful, some don't know, and more than half said, no, not useful. So here's a huge divide. You have the same data, the same issues, but two different communities really looking at that opportunity from different perspectives. And that's really, the environment that our HACAST team launched in back in 2010. At the time, and for a long time, NASA has funded science teams. And the way that science teams work is that there's a solicitation put out to the research community to get research funding around a specific instrument. And because once the instrument is up in space, they want researchers to use the instrument. But back in 2010, they tried something new. Instead of funding around one instrument, they instead funded around the problem. And this was this idea of an applied science team. And so the first applied science team that they launched was around air quality. And this was called the Air Quality Applied Science Team, which we call ACAST. And ACAST was led from 2011 to 2016 by Danielle Jacob at Harvard. And I was the deputy lead of that team. In 2016, it was recompeted, now with a focus on health and air quality. And this expanding of the title also led to a somewhat broader mission, that instead of only looking at regulated pollutants, we could look at issues that were relevant to health that might extend beyond regulations, such as pollen or wildfire smoke or extreme heat. And we also, with the advent of HACAST in 2016, while we stayed focused on the United States, also started looking at global issues, because most of these satellite data sets do cover the entire globe. That tempo that I showed you is only North America, but most of the other data products that we've been looking at actually cover the whole world with a once a day or so snapshot. Our current generation of HACAST, which is sort of just ended or is ending, is the third generation. We're waiting to hear whether NASA will continue to fund this effort. But its mission has been to connect NASA science with end users. And they've done this both by the proposed projects that people wrote about to try to get onto the team to begin with, as well as recognizing that most real world problems need a responsiveness and an adaptability that is not characteristic of most scientific work. And just to sort of zoom out for a second, I'll describe that the typical science process when it comes to funding is that the researcher writes a proposal and maybe hears back 6 months later if it got a yes or no. And if it got a yes, then they begin to recruit a graduate student, which might take another 6 to 12 months. Then the graduate student starts, but they're taking classes, things go slow. You're not really getting research going for maybe 2 or 3 years. But this process of an organization who comes to a university with a problem and then to say, okay, we'll get back to you in 3 or 4 years, this usually is not the same timeline that operational organizations need. So one of the things that was unique about the ACAST and HACAST mission was this recognition that there would be a responsiveness and an adaptability built into this project. So I mentioned ACAST, I mentioned HACAST. From NASA's perspective, they know that when they fund research, good stuff will almost always come out of it. But what they were interested in with this team structure is sort of what is that marginal value of having a team organization instead of funding 14-ish PIs on their own. And what we found is that this team structure really makes a difference. It increases the visibility of our work to end users, and so that we could go out and build relationships around this topic rather than relying on Professor X or Dr. Y at different institutions to individually build their own networks with air quality managers and health professionals. We built a culture that supported and promoted a two-way dialogue where we're very much listening to user needs, not just sharing as a one-way messaging, and also understanding emergent issues so that we could tackle them. One of the things we found is that if you have a group of 10 or 15 researchers and their collaborators, even if a topic comes up that's not exactly in one person's expertise area, there's enough overlapping expertise to be adaptable and responsive. Sometimes the exception proves the rule, and over the years, sometimes it has come up about volcanoes in Hawaii. And actually, there really was not that much overlapping expertise around volcanoes in Hawaii. So that's something that we did a little bit of work on, but not a ton. But almost every other issue, whether it's warehouse facilities or offshore ports or urban growth or power plants or chemical sensitivities, there's been enough people on the team that we could mix and match to address a wide range of challenges that have come up in conversations. And one thing that I found really exciting about this process as well is that we would meet every 6 months around the country. And we could hear when something worked and a stakeholder was saying that it was really important for their agency, or a researcher was sharing some new approach, there could be a quick contagion of that knowledge and success to quickly spread. So these were the PIs of our most recent team from, some of them I know have spoken here in previous Wierman lectures, and others are spanning literally from Alaska to Florida. We've also built this network of these professional air quality and health professionals. We have over 2,000 people on our mailing list. About 300 people come to each of our meetings every 6 months. About a third of the attendees at the meeting, it is their first meeting. So we're really trying to grow the community. But we've also realized that sometimes there were these super users, folks who were coming to our meetings, active in advancing ideas. And so we started this HeyCast Ambassadors to just have a platform for people who wanted to be extra involved. And this also provides a nice cross section. I'm seeing, if HeyCast were to continue, I'm seeing people in this audience who probably themselves should be on our HeyCast Ambassadors. But I think that, so this is a snapshot, but of some of the types of organizations that we've been working with, the EPA, different states, energy organizations, private sector companies, and nonprofits. So this idea that there could be, should be connections between air quality management and science was also a topic of the UK analysis. And the question though, have you ever collaborated with the other group? And the answer among scientists was no. Even for scientists working in air quality, 80% had never actually collaborated with these outside users. And not surprisingly, about 75% of outside users had never collaborated with the scientists. But to me, one of the nice things is, do you want to? And here the answer was overwhelmingly positive on both sides. So there's a real desire to collaborate, even though that hasn't happened. And so, I think it's interesting before moving on to talk about some of our collaborative work to also recognize why this isn't as widespread as it might be. And a big issue is funding, because while this NASA initiative was structured to require this collaboration, most funding mechanisms are not. And also it does take a lot of time to build effective partnerships, especially when you're really focused on listening and coming as equals to the table. The stakeholders had similar, but a little bit different perspectives, lack of communication, a lack of understanding. And I think here it also speaks to the need to be listening, to understand different perspectives. And also, where is the benefit? Because I think we're researchers, our job is to answer interesting questions and to advance science. That is not the job of a lot of professionals working in air quality and health. Their job is to do analysis that meets regulation, or to keep people healthy, or to meet with clients, or whatever the case is. So I'm going to use this all as a launching pad in the second half of the talk to share with you a few examples of work from my group and some broader themes that kind of, I think, maybe play out how this two-way dialogue has taken shape. And to start out, I'm going to introduce this idea of ground level ozone. Ozone is an interesting chemical because a lot of people have heard of it in the context of the stratospheric ozone layer, where it is good and protects us from incoming solar radiation, and acts as a natural sunblock. But just like you don't want to drink your sunblock, you don't want to breathe ozone near the surface. So we often say ozone is good up high, bad nearby. And nearby, it's associated with respiratory disease. It can degrade rubber. It can shorten life expectancy. And it is one of the 6 main pollutants regulated by the EPA with a limit, where you're either passing or failing. And this is the latest data from the EPA. I'm zooming in where we are here on the eastern seaboard, just to show you that ozone is a huge issue. Each of these dots represents one of those gold standard monitors that we mentioned earlier. And while most of them are blue, meaning that they're passing, the red dots indicate failing. And back in 2018, I believe, the counties that had one or more monitors in the red were designated as failing. And that is what is the red here. And if you live in one of those counties, you probably take your car to be emissions tested, or companies probably are subject to more stringent air regulations. So it differs by state. I'm not sure exactly what it is in Maryland. Other folks could speak more. But just to give you kind of the broad outlines of what the passing or failing typically involves. So we see that there's high ozone levels, but the question is, why are there high ozone levels? Ozone is not emitted directly by smokestacks and tailpipes. It cooks up in the atmosphere. And it cooks up from two main ingredients: nitrogen oxides and volatile organic compounds. Now, nitrogen oxides are emitted by anything that burns, and volatile organic compounds are in a category of evaporative chemicals. When you smell the smell of pine walking through a forest, that's a VOC called alpha pinene. If you're painting your house and you go to the paint store, you have the option of less smelly or more smelly paint. The less smelly paint is low VOC paint or no VOC paint. So when you think VOCs, think smelly evaporative chemicals. NOx are combustion products. And one way to think about the trade-off is that each is shown with this graph is called an ozone isopleth graph. And the idea here is each of these lines represents a value of ozone. As you go in, it's higher ozone. And what it's suggesting is that you can get the same amount of ozone with a lot of VOCs and not so much NOx, or with a lot of NOx and not so much VOCs, or with a medium amount of both. And this is a challenge for thinking about how to control ozone, because the question is, do you control the NOx, like requiring cars to be emissions tested, or do you try to control the VOCs, first going after industrial processes like a printer? And each of these are hundreds of millions of dollars, really per facility policies. So you don't want to screw it up. You want to know that if your goal is to reduce ozone, you're reducing the right compound. One kind of metaphor that I find helpful is thinking about if you're baking a cake and you only have, 2 eggs and a cup of flour, maybe you can make one cake. But if you have lots of eggs and 1 cup of flour, and then somebody gives you twice as many eggs, that doesn't change the number of cakes you can make. You're already saturated. Your egg needs are met. And that's one way we think about it with ozone, that you can be NOx saturated if you have a lot of NOx, like in an urban environment, and you can be VOC saturated, and where the VOCs don't matter anymore, if you're outside of an urban environment where there's a lot of trees. Now, even though we have quite a few ozone monitors, we really have hardly any NOx monitors or VOC monitors. When I say hardly any, about 500 NOx monitors, and I think more like 300 VOC monitors, but that's spread all across the United States. So it's really not as many as you have ozone. But what we do have, as it happens, is satellite data for NOx in the form of NO2, and satellite data for VOCs, a particular VOC called formaldehyde. And what we can do is look at the ratio of these two satellite products to determine whether it is limited by NOx, where changing the NOx is really going to tackle the ozone, or whether it's limited by VOCs or NOx saturated, where changing the VOCs will change it. And this line of analysis has been taking shape for quite a while. Back in 2002, Sandy Silman at the University of Michigan first laid out this idea that NOx and VOC ratios could be used as an indicator for the sensitivity of ozone formation. And in 2004, Randall Martin and colleagues applied satellite data to determine this ratio. Then in 2010, my colleague Brian Duncan, again, a previous Wierman lecturer, had applied that to what was at the time the best satellite data from something called the Ozone Monitoring Instrument, or OMI. And I was, excited. This was 2010. This was right at the beginning of the first ACAST team. And one of the things that we would do at these ACAST meetings, first of all, is we would beg air quality professionals to come to the meetings because they were really not interested in coming to the meetings. But we would say, please, please come to the meetings. And then sometimes they would come. And when they did come, one of the small talk things that I would like to do is to ask them, do you use satellite data in your work? And the answer was always no, 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 until I asked one air quality manager from Colorado. It was when we were having a meeting in 2012, I believe, in Wisconsin, and he'd flown out for it. And he said, yes. He said, I love satellite data. You do? What do you use it for? And he said, well, I found Brian Duncan's 2010 paper for ozone sensitivity. And I downloaded the data and I followed along exactly what he did. And I presented it at a meeting of the regulatory board for the Front Range of Colorado, because there was one group who emitted NOx that was saying that it was mostly VOC contributing, and another group that emitted mostly VOCs that was saying it was NOx control. I mean, this is obviously a bit of a political football if you have no information. And so he did this analysis to support effective science-based policymaking in Colorado. And I thought this was such a cool idea and very unusual to be digging through the academic literature, that I worked with Pat and English major at the University of Wisconsin, who I was working with, Sarah Whitman, to talk about his experience, and it was published in the magazine of the Air and Waste Management Association back in 2014. But hearing how Pat was using this for his own policy analysis really, made me excited to do the same thing. And so I had a student from China, Xiaomeng Jin, and she wanted to analyze energy issues in China. We were discussing where can you get good data that can allow you to answer energy questions in a new way. And I said, well, why don't we take this approach from Brian Duncan? Follow the example of Pat Reddy. Why don't we do that for China? And so we did do this analysis for China. We published it in 2015. And actually, Xiaomeng Jin has continued to then keep analyzing this question of ozone sensitivity. She's now a professor at Rutgers University and really probably the world leader on using ozone sensitivity from satellite data. She continued to analyze it during her PhD at Columbia University with Arlene Fiore, and she started to come up with better ways to figure out whether how to interpret the data in a physically and chemically consistent manner. And this work then kind of took a step forward, in my opinion, in 2022, when we began looking not just at average ozone, but what about ozone on the dirtiest days? On the dirtiest days, is it limited by NOx or is it limited by VOC? And this was a paper that was led by Madame Kui Tao, also at Columbia University. She did her undergrad at Wisconsin. I work with tons of undergraduates at the University of Wisconsin. So many of them end up going into these fields like Madame Kui did. But she was looking at these high ozone days. And this was definitely the kind of analysis that air quality managers needed, because air quality managers are interested in overall sensitivities, but really you're interested in what's happening on those dirtiest days that are going to flag non-compliance. And Tauma's analysis was only for New York. But it was also done in a very high level way, downloading the data using Python and complex analysis. And I wanted to figure out, is there a way to make this type of analysis accessible to professionals who might want to use it? So I worked with an intern of mine, Jennifer McGinnis, and I asked Jennifer to first of all survey the existing tools that were available to look at satellite data. And the common tools are up on the far left column, where NASA Worldview is very user-friendly. It gets a green for ease of use, but it doesn't allow for any of the more complicated ratioing or averaging that we need to do. And as you move down the list, different platforms have different benefits, but none of them can do everything until we came to Google Earth Engine. And actually, at the time, I had never heard of anyone, researcher or practitioner, using Google Earth Engine as the interface for these NASA satellite products, even though obviously somebody had thought to put them into that framework. Jennifer wrote a how-to on how to do it, and we published another article in the magazine of the Air and Waste Management Association, a practical methodology using Google Earth Engine. And we recreated the New York analysis of Tao et al. We also did it for Denver, and we came up with a way to flag what were considered high and low ozone days using a metric.
Okay. Yes.
That okay. Anyway, this is data that the EPA puts out in a very user-friendly form, so anybody could go through and quickly filter the days using these existing data products. So once Jennifer put out her tutorial, and we shared it at a HeyCast meeting in 2023. Actually, it was only a couple of months until the next HeyCast meeting when we started to see air quality managers from across the country now sharing how they were using Google Earth Engine to access satellite data and to do this kind of ozone sensitivity, which was incredibly fulfilling. And so I took a photo of Dr. Chola Regmi from the Texas Commission on Environmental Quality, talking about how they were following along this model. And one person who had also seen it and was also following along was, you may remember his name, Pat Reddy from Colorado. Because he knew how hard it was to download and process satellite data. And so when he saw the potential for Google Earth Engine to make this process way easier, he got going. And not only did he use it for ozone, like in our tutorial, but he started to use it to track wildfire smoke. And so then in about a year ago, in spring of 2024, Pat and I both spoke at a meeting in St. Louis on helping air quality managers understand tools that were available to track wildfires. Because you may remember back in 2023, there was so much burning in Canada, lots of smoke events affecting the whole United States. And this is a huge deal because the way that the Clean Air Act works is you're either passing or failing. And so if you have a lot of smoky days coming in, your county, state is at risk of failing. And you might say, but that's not fair. It wasn't our fault. It was the fires in Canada. And then they say, yes, that's right. So you can prepare a 150-page document describing how it's not your fault, and that's called an exceptional event demonstration. And there actually is no rule book on how to prepare an exceptional event demonstration. So typically then you, air quality manager, might hire a consulting company to do it for you. So now they're spending about $100,000 or more, maybe just to show that one day and one monitor isn't their fault. And with all of these smoke days across the United States, that is simply not a viable path forward to think of, and with fires increasing and more regular. So Pat had used Google Earth Engine to begin to diagnose these exceptional events and create a toolbox that could be used by state agencies. And because NASA really wants to lean in to the successes and fund projects that could have a real impact, NASA funded me and Pat to work together to build this toolbox to support exceptional event demonstrations. And Pat really has been working to lead this effort, looking at 20 or more layers of data in Google Earth Engine, coming up with different flags. It's already been used to support exceptional event demonstrations in Jefferson County, Alabama. It's being used in Phoenix this summer, and it'll be available publicly next month. Just to give you an idea of what this looks like, there's these layers of data. The right is for the left is for PM 2.5, the right is for ozone. And Pat has come up with a number of new diagnostics that can be used to help identify these. I won't go into the details here, but just to say that this has, in my opinion, been an exciting trajectory where one user need has led to a scientific innovation, and then the scientific innovation has led to another need and has led to sort of a breakthrough in new ways to analyze data to be attributing air pollution to wildfires. So because I work with so many undergraduates, I have honed kind of a philosophy of STEM, if you will, not to get too big picture, but I really don't like the metaphor of a leaky pipeline. You may have, if any of you have ever thought about STEM workforce development, it's often described as a leaky pipeline where a certain number of 18-year-olds declare that they are going to major in science, technology, engineering, or mathematics. And over time, they fall out of the pipeline. And women fall out of the pipeline more than men, and minorities fall out of the pipeline more than the dominant group. And so over time, you have a pool of potential scientists who gets smaller. But myself, I started college with zero interest in science and math, and I got pulled in. And so I've always been interested to say, like, air quality is such a great plug-in point because it's political and it's health, it's equity, it is artistic and mapping. I mean, there's a lot of plug-in points. And so I like students to be able to get involved in research in my group without saying, well, first go take the introduction to Python class and go take differential equations. I don't want to be telling them to come back in 2 semesters because they will probably never come back. Instead, I'd like to have an on-ramp that the students can get on right away. And to make that on-ramp, we need the students to be able to use Python. And so we've written, I should say we, 2 of my graduate students, with my blessing, have written a series of Python tutorials that are intended for students who have zero background in computer programming, because our question was, can we make the Python easy too? And so one of the ways that these tutorials have been so effective is because even folks who are computer science majors have not been exposed to the data formats that are typical in atmospheric science and air quality. And so even for students with a strong computing science background, they move through these tutorials pretty quickly. Students who've never had any background, they move through slowly. Maybe 6 months ago, I asked our IT guy, I said, hey, could you tell me how many times these have been downloaded? Because I thought maybe it would have been like 10 times for our research group, maybe 15 times with some of their friends. But actually, it was hundreds of times. And we plotted up who's been using these Python tutorials, and it's all around the world, which has been super cool. So yeah, so I think this idea of, you know, empowering people who want to use the data to do it in whatever way fits their needs, whether it's learning Python, Google Earth Engine, or navigating some of the other available tools. I'm just gonna throw in, this is my last little pie chart from our friends in the UK, but I think it's also relevant to this conversation because they had asked, how do you like your data? And the scientists and researchers want it in the raw format. They want it so they can manipulate it. That is exactly not how most professionals want the data. They want it in Excel data sheets or GIS or pre-made graphics and so again, I think just recognizing that even if we're all using the same data for the same problems, there can be these cultural divides. One other example of our data using, partners to inspire our work. I've been working with the American Lung Association. They are also using that ground-based data from the EPA, but where the EPA is interested in passing or failing, the American Lung Association says, well, maybe you're not failing, but maybe you're getting a D or a C. You may not be getting an A. So every year, the American Lung Association comes out with their State of the Air report. It's a very big deal. They give a grade to every county with a monitor, which is only about 20% of all US counties. So they've been very interested in, could they be giving grades to other counties that don't have a monitor, and could satellite data help them with that process? So I've been working with them for maybe 5 years, and at the end of last year, they came out with their first report based on our work, talking about how satellite technology can hold promise for counties without monitors. They came out with another report about 2 weeks ago, analyzing equity with satellite data from some of the work that we've done. I can talk more about that, but I want to not end our time together without also talking about one of my favorite topics, which is models. And a lot of this work actually comes from the work of Tracey when she was a master's student with my group. And when we think about air quality and computer models, there's actually a very complex landscape of tools that are available. And often people only know the tool that they've used before or is in their kind of wheelhouse. And so I thought it would be helpful, and Drashti prepped this really nice kind of mapping of data models with the idea that you have some local needs, like if you want to look at one individual facility. You may have regional needs if you want to look across a couple of states, but really see individual cities and suburbs. And then you have global scale needs where you have bigger grid boxes that you may not be able to parse out intra-city changes, but you could look at what's happening continent to continent and on a larger scale. And there's really 3 different types of models that can address these cross-scale problems. One are the advanced models. Those are the fluid dynamical models with explicit treatment of chemistry in orange. Then you have models that can handle the dispersion in a simpler way, and that is green. And then you have what are called reduced form models, which are kind of derivative models where you sometimes take the complicated ones and pull out the key statistical relationships. And those are blue. And these advanced models, are really the state of the art for good reason. They are based on numerical analysis of partial differential equations with fluids and chemical processes. They are the only tool that is available for chemically created compounds in the atmosphere like ozone. And they are by far the best. So I want to start there and saying actually most of my career has been spent with these state-of-the-art models. And if you look at the scientific literature, most of the scientific literature uses the state-of-the-art models. That AirMod and HighSplit are 2 examples of dispersion models that are there on the board of scientific research, but further down. But it's hard to know what people are really using out in the world. But one of the metrics I like is Google Trends data. And so just because I like to update this before each talk I give, this morning I reran the Google Trends analysis for these 5 major models. And really it is the simplest model, the AirMod model, which is probably used many more times over than the fancy state-of-the-art models. And I think this is relevant to thinking about data and decision-making, because when you have the scientific community focused on the elite type of models, but then you have all these people using models that may be holdovers from the 1990s, I think there could be a lot of room to improve. And this AirMod model is a Gaussian plume model. Just to show you what that means, it is literally like a Gaussian cone coming out of a facility. It doesn't twist and turn with the wind, but it does change hour by hour or less than that as the wind shifts. If you look at work that how a specific facility, and this is from Tracey's work too, compares. On the left, you have the state-of-the-art fluid dynamic model, CMAC, which gives you grid by grid, and you can kind of see that on the day in question, there's higher pollution to the eastern side of this domain. But with the AirMod model, you can zoom in and you start to see very high concentrations right near the source that you just cannot get with the coarser scale model. So I'm going to skip over some of this in the interest of time, except to say that work we've been doing recently has been funded by the Natural Resources Defense Council, NRDC, who is interested in analyzing certain facilities. And in this case, they're very interested in liquid natural gas terminal facilities in the Gulf of, I forget. And so they were paused under the Biden administration, in part because there was concern about the air quality impacts to communities living near these LNG terminals. However, there was no quantification, or at least no robust quantification of these health risks, because it was so local, it didn't fit the widely used health analysis models. So NRDC funded us to take this AirMod modeling system and add a health analysis to it based on EPA methodologies, and add an equity analysis to it based on emerging norms in the literature. And we've done this. And actually, what we do is to set up the census tract or block group level, and to run AirMod specifically to get the concentrations in these areas. And what I think is really exciting is I alluded to this work at a meeting in Washington, D.C. in December, and actually was approached by someone from the US Army who said this was exactly what they wanted to do too. And so now I'm in touch with both the Army and NRDC, who are quite different organizations, but who are interested actually in the same approach. And so this is sort of a direction that we're moving in to, again, try to improve the methods that are out there and make them as relevant as possible for problems. And so just to have time for questions, I'll end there, and happy to answer questions or follow up later. Thank you.
Maybe we can take one or two questions.
Thank you so much for your talk and for your visit, certainly, to Hawkins today. I have both a point and a question. The point speaks to the tutorial you've been developing in your group. Those are very effective to providing tutorials to the public, but they are also very effective at the Goddard DAX to have tutorials and how-tos sitting next to the data. And so I think PayCast is archived with Justice, I think, or just a NASA DAX, wherever it's archived, having links to those tutorials where data users of different disciplines are coming to grab your data and may not necessarily have the tools or skills to play with that data effectively for their purposes, is something that could be of interest or relevance. I see that a lot in the carbon world specifically. And so then my question is sort of taking a step back towards the first half of your presentation. You spoke about sort of the scientist and researchers domain versus the data users and the public domain, and talking about how there is interest on both sides to interact. And there could be synergy, but there is just no, a lack of collaboration at this point. And I wanted to get your opinion on what really is the blocker between that. And I know you had a couple of points saying, funding, et cetera. But my takeaway is that it's time that scientists and researchers, everyone wants to be on the decision-making timeframe, but scientists and researchers inherently are on a different time frame, working up the data, the manpower, the nitty-gritty coding, versus the data users who, the stakeholders who need the data and the data users who want the data automatically. And so what are your thoughts, on a commonality between the two at a really fundamental level? Maybe is it time, or is it a specific species of air pollutant? Like, is there like, would we need like almost like an emergency air pollutant to really bring the two people together, those two communities together?
Yeah, I think it's a great question. And, the barriers that I listed were from this social science study in the UK.
Right.
Now I'll give you my own opinion. Honestly, I think it is a lot. I think the barrier is the motivation. Why are you doing what you're doing? And I often talk to researchers who want to work with companies or nonprofits. And so they say, well, I just want to tell them about why my science is so interesting. And that is a perfectly fine thing to tell if you're at an academic lecture or at a scientific meeting. But if somebody from a company sits down with you for 15 minutes and you just are talking at them about how cool your science is, that is not the recipe for an effective partnership. And I think that it's a lot understanding that why people are doing, a company may be doing their job to make money. Air quality manager may be doing their best to bring their state into compliance with air quality regulations. And so I think to me, part of it is like getting on the same page with what are we here for? And sometimes a scientist might say, it is not my job to make this company money. Like, that is not my job. In which case I would say, it isn't your job. Like, good luck. Like, you go do you do you, they'll do them. You do not have to work together. So I think that part of it is to say, can we find common ground that we both care about and that we both want to do? Because, oftentimes I talk to scientists who say, but is this publishable? And it may not be publishable because it's too politically sensitive. It may not be publishable because it's not new science. It's just taking something that was done someplace else. And if it's not publishable, then is it appropriate for graduate students to be doing that for their PhD? I mean, and so on the one hand, like I agree with you, it is time. But I think part of it is sort of, what is the time that you're paid for? What are the things that you're willing to do, even if they're not part of your job? And, many of the, I would say, participants in our HateCast activity from the perspective of the air quality managers tend to be individuals who themselves either like science, like NASA, like are excited about this. They're usually not there because they're required to be there. They're there because they're choosing to be there. So now we've said, okay, these people, it's not exactly your job, but you're taking the time to do it because there's a shared interest. And maybe you have a graduate student who knows that they're not going to get a publication out of this, but that they want enough to work with real world organizations that they stretch. And now we've met in the middle with a shared interest. But yeah, I guess I would just say that, recognizing that different organizations have different motivating missions.
Yeah, and maybe it's a factor of urgency that would link to those two communities together, that, and what is more urgent than, maybe I'm biased in the field, but maybe what is more urgent than air quality? So
that's a good place to end up. Yes.
Thank you so much for your talk.
Thank you.